Regulating hemostasis. This is probably one of the most challenging lessons that I've had to put together for quite some time. Figuring out exactly how much information to put in here and how to organize it to make it easy to sort of associate all of this stuff in your head. And I wanted to make sure that I put enough in here that you truly understand how profoundly complicated the whole hemostatic process is. The absolutely interconnected series of checks and balances and feedback that not only balance the need to stop hemorrhage with the need to keep the clot from occluding the blood vessel, but making sure that all of this is happening only at the site of injury. So here's our basic coagulation cascade that we learned in the last lesson. We split it into the intrinsic pathway, the extrinsic pathway, and the common pathway. All of this is taking place on the surface of the damaged tissue. Remember, the exposure of collagen in that subendothelial layer is what starts this whole thing. That is what the platelet, via the von Willebrand's factor, adheres to. And that is what starts the activation and starts primary hemostasis. Then once those platelets are activated, on the surface of these activated platelets, we get this secondary hemostasis, this secondary reaction where all of these plasma proteins come together to make fibrin, which is what binds the clot together. Now, when we learn this, we basically learn it in a relatively linear fashion. So we've got our boo-boo here that causes the tissue factor and the 7 to get together. Smaller. If we add a little calcium and some PF3 for some phospholipid, this little mess becomes our 10-ACE, and it activates factor 10. Then, if we go over to the other side, on the intrinsic side, 12 activates 11, which hits on 9. So 9 and 8, we put those together with a little bit of von Willebrand's factor. Again, some calcium and some platelet factor 3 for our phospholipid. That is our other 10-ACE. And it goes down and it activates factor 10. Then once factor 10 is activated, the 10 and the 5 get together again with some calcium and some platelet factor 3 for our phospholipid. And they activate prothrombin to thrombin, and then thrombin makes fibrinogen into fibrin, and we have a clot. A fairly linear sort of thing. Well, that isn't exactly the way it happens, because once we've got thrombin made, the thrombin says, well, I don't think things are going quickly enough. So the thrombin comes in here, and the thrombin, so it goes over here to factor 5, up here to 8, and over here to 11, and says, hey, let's step up production. Let's get things going a little bit faster. And once there's enough of me, I'm going to go ahead down here and bind with some thrombomodulin. And oh, by the way, factor 13, you need to do your job too. And we're going to bind with the thrombomodulin, activate the protein C. Well, the protein C is going to go, I think we got too much going on. 5, you need to slow down. 8, cut it out. And when this happens, we're also going to see the antithrombin 3, and the antithrombin 3 is going to say, 10, stop what you're doing. We've got too much activity. We're going to make too much of a clot. And thrombin, I am going to tie you up so that you can't do anything else. And the tissue factor pathway inhibitor says tissue factor pathway, you're done. You're not going to do anymore. We also have a whole bunch of other little proteins that put in their 2 cents worth, and they say, hey, you contact factors, you need to cut it out. And they come in and they say, oh, this is no good. You can't do this. They'll inhibit the factor 10. They'll say, hey, fibrinogen, no, you've got to stop what you're doing. And there's several other feedback loops that are in here, and it says, no, not this, not this. This is more what it really looks like, is all of these checks and balances and this kind of very messy mishmash of things acting and reacting and interacting with each other. So this is a much more complicated process than the very simple linear pathway that we initially use to learn the process. And it all happens at one time. So it's not like this happens and then this happens. This happens, this happens, this happens at the same time as this and this and this. So it all happens at one time. So we need to discuss a couple of definitions, and that is, what is a feedback loop? A feedback loop is not unique to coag. It's not even unique to biological systems. A feedback loop is any time where a product, either an intermediary product or the end product, goes back and affects the rate of the reaction that created it. In a positive feedback loop, the intermediary product or the end product, whichever, goes back and acts on a earlier step of the reaction and intensifies the activity. In a positive feedback loop, we get more activity. It increases, enhances what's going on. In a negative feedback loop, these are an inhibitory feedback loop. So the more of something that is made, the more it's going to slow down that reaction cycle so you don't make too much. So a negative feedback loop is inhibition, and a positive feedback loop is an intensifying. So of all the regulating proteins that are out there, thrombin, and thrombin. What does thrombin do? Well, what doesn't thrombin do? In our little pathway, we came up with the fact that it converts fibrinogen to fibrin, and that it activates factor 13 to stabilize that fibrin. Well, and frankly, for a long time, that's all that they knew it did. Well, they've come up with some more stuff. It is both a procoagulant and an anticoagulant at the same time. A lot of these functions depend on the concentration of thrombin that is present. So thrombin is a very strong platelet agonist. That means it goes back and activates platelets. It does that by binding onto certain sites. I don't care if you remember what the binding sites are. But thrombin goes back and initiates clotting again. So one of the end products of secondary hemostasis is the activation and restarting of the primary hemostasis. The other thing thrombin does that is a procoagulant activity is it has a positive feedback loop with the intrinsic pathway. It enhances the activity of factor 8 and the binding of 8 with 9, and it also activates factor 11. There's another positive feedback loop of thrombin and factor 5. So to speak, thrombin sort of goes back and tells its daddy to do more. So it goes back to factor 5, which is what initially was used to make the thrombin from prothrombin, and increases the amount of 5, which is going to increase the amount of thrombin. Now, as the thrombin increases, some of these anticoagulation functions occur. Thrombin is partially responsible for releasing tissue plasminogen activator from the endothelial lining, and we'll talk more about that in the lecture on fibrinolysis. It also binds with a protein called thrombomodulin, and the thrombomodulin thrombin complex activates protein C. And we'll talk about that in just a minute. As the thrombin continues to increase, the high levels of thrombin are going to act on plasminogen and turn it to plasmin, and plasmin is what is going to break down the fibrin clot. So just as the fibrin's being made, it is starting the process to tear it down. We have several natural anticoagulants, and these are all within your body at all times. I've kind of put them in blocks because these sort of work together. So the first is that thrombomodulin we talked about, and that complexes with thrombin to activate protein C. And if you think all the way back to when we were talking about why doesn't the blood just clot up while it's flowing through the blood vessel, this was one of the methods that a healthy endothelium uses to keep the blood flowing. And that is that thrombomodulin and thrombin complex, which activate protein C. So the activated protein C with its cofactor protein S is going to inactivate the labile factors 5 and 8. And it's a good thing to remember that 5 and 8 are the two that are broken down by heat, because that's going to come back to see us again when we get into blood bank. The second group of proteins are heparin, along with its cofactor, heparin cofactor 2, and antithrombin 3. So heparin is a natural chemical which is released by mast cells in the tissues, and we'll get into hematology next semester and talk about basophils in the bloodstream, which become mast cells when they move into the tissues. These mast cells release the heparin at the site of damage, and then together with their cofactor, they stimulate the binding of AT3 with thrombin. Antithrombin 3 makes sense what it does. Antithrombin 3 binds to thrombin. And it's important to know that this is an irreversible bond. Once the antithrombin 3 hooks on there, that molecule of thrombin is done. It's never going to do anything else again. It's bound up, it's become garbage, and it's just going to be removed from the system. The antithrombin 3 also blocks the activity of 9A, 10A, 11A, and 12A. The next relatively potent inhibitor of coagulation is tissue factor pathway inhibitor. And again, this isn't a particularly clever name because the tissue factor pathway inhibitor inhibits factor 3 pathway. So it inhibits the extrinsic pathway by interfering with the tissue factor and factor 7 complex. It also directly inhibits factor 7, and it partially inhibits factor 10. Then the last of the natural anticoagulant methods, as fibrin is broken down into its component parts, we get something called fibrin degradation products or fibrin split products. These products themselves actually inhibit fibrin formation. So as the fibrin is broken down, what it's broken down into becomes an inhibitor of the entire process, so a negative feedback loop. We have another series of proteins, and these are referred to as serpins or serine protease inhibitors. There are tons of these in tons of animals throughout the entire world. And they do a lot of different things. But basically, what they do is they go through and they inhibit the enzymes and their actions. So I've listed the names on the left-hand side and then what their target is. Protein C inhibitor, again, not a particularly clever name because protein C inhibitor inhibits activated protein C. That one kind of makes sense. C1 esterase inhibitor basically inhibits the contact factors, 11, 12, and the kallikrein, and it also inhibits plasmin. Alpha 1 antitrypsin and alpha 2 macroglobulin inhibit the contact factors, thrombin, plasmin, and they also inhibit TPA or tissue plasminogen activator. So they're going to help to kind of put the brakes on the fibrinolytic process. Protein Z dependent protease inhibitor, along with its cofactor protein Z, which is why it's protein C dependent. But this is a direct factor 10 inhibitor. It inhibits activated factor 10, and it does have some action on factor 11. Plasminogen activator inhibitors, or PAI, we're going to talk a lot more when we talk about fibrinolysis. They inhibit plasminogen, again, not a particularly clever name. And alpha 2 antiplasmin, antiplasmin is going to react against plasmin. So, didn't have very creative people coming up with the names on some of these. If you're studying well and things are going well, you can learn all of this. This would be wonderful. I would not spend the bulk of my time here. Yeah, there may be one question on the test. This is going to be fairly minimal as to what I'm going to test you on with. Okay, so not only do the coagulation proteins work on each other, but there are certain chemical communicators from other systems that are going on that also help regulate hemostasis. And this first group are the proinflammatory cytokines. This is one of the cases that we will run across several times throughout your course of study, where the other subjects all mesh together. In fact, all of the subjects mesh together. And this is where serology or immunology and coag meet. Unfortunately, we haven't had immunology yet. So super quick, anytime there is damage to a tissue, the body responds with something called the inflammatory response. A variety of things happen. The most important ones are that we get an increase of white cells at the site, and we get an increase in what we call acute phase reactant proteins. One of these acute phase reactant proteins is fibrinogen. So this kind of starts to show us that there is a relationship between inflammatory conditions and an increased risk of thrombosis. But for now, we're just going to talk about what exactly happens, and that is that these inflammatory cytokines, which are just chemical messengers that are put out by certain cells, do a couple of things to regulate hemostasis. They increase the adhesion proteins, so they're going to encourage primary hemostasis. They're going to increase tissue factor production by the endothelial cells, which means that we are going to see increased extrinsic pathway activity. They're going to decrease protein S, and protein S, along with its cofactor protein C, are anticoagulants. So this is going to increase the amount of coagulation that is happening. It's also going to increase the plasminogen activator inhibitor. And so basically what's going to happen is if we inhibit the activator, then the plasminogen isn't activated. So we're not going to get a breakdown of the clot. There are other chemokines that we see during damage to the blood vessels. They also activate platelets, and then they kind of send out the message to the white cells, the leukocytes, that, hey, you need to get over here, we've got a problem. Then when the leukocytes get there, they also activate platelets. They release something called neutrophil elastase. They stimulate secretion of the thrombomodulin from the endothelium. That's the thing that the thrombin binds to activate the protein C. And they also inactivate 13. So even though we're going to see some increased fibrin production, it minimizes the amount that is stabilized by the 13. So the positive feedback loops here, factor 11A increases activation of 11. So we have thrombin that's going around doing its thing. Then we also have this activated 11 through A, which activates 11 to make more 11A, which activates 11 to make more 11A, which activates 11 to make more 11A. We also see an interaction between the extrinsic pathway and the intrinsic pathway when the tissue factor and 7A come over here and activate. So these guys together come over here and activate 9. So and that's how the extrinsic pathway actually initiates the intrinsic pathway. The negative feedback, our tissue factor pathway inhibitor inhibits the tissue factor pathway. So we're going to have inhibition here. We're going to have the antithrombin here acting on 10 and binding up thrombin so that it can't do anything. The antithrombin also is going to go over here to 9, 11, and 12, 9, 10, 11, and 12, and kind of knock out this intrinsic pathway. And that's it in a nutshell. There are other feedback loops as well. There's other proteins that can be involved, but I think this is complicated enough. So go through it a couple of times, work on it, draw your own pictures. That usually helps quite a bit, and there are some decent videos out there, and I will put those links up when we are ready to kind of watch them all together.